Yes, maybe 2 minutes more. We can wait for our research council members and to join, and then we'll start.
All right. Mm-hmm. Mm-hmm.
Yes. So, Professor Kumar, could you be online?
I am. Can you see me now?
Yes.
Oh.
Thank you. Very good morning and good evening, both. Namaskar and very good morning to today's distinguished speaker, and good evening, my dear colleagues, distinguished members of our research council, invitees, our former directors, and friends. We have great privilege of having a very, very eminent professor of computer science whom we have interacted during the Indian diaspora meeting, Summit Vaibhav, and with interaction, we are following to evolve a program where machine learning and artificial intelligence can be utilized in the earth sciences. There cannot be a better opportunate time than this to have a person of Professor Kumar's stature, whom in the present era, when we most of us count citation and the impact factors and so on, I was just looking to the updates, and I found that his X factor now is 125 or so, probably amongst the few highest cited researchers in the world. Professor Kumar is equally a kind person and very helpful for the people of the Indian origin. Last time when we have requested him, he has agreed, and this time also he has been kind enough to agree to deliver a talk in the very early morning hours of United States. He is an engineer by profession and alumni of University of Roorkee, now IIT Roorkee, and had a lot of connect with Indian researchers, as well as very important connect with us is his several books which are written recently, utilizes machine learning and artificial intelligence for the data mining towards the management of the water resources. And he chose to speak today on a very important and dear problem for us, which not only our country, but whole globe is trying to find solution for. So with this brief remark, I take this opportunity once again to thank Professor Kumar for being with us today and sharing his long experiences and very eminent scientific knowledge on the utilization of the and possibilities of the machine learning for the science of water. So may I request our colleague, senior colleague, Dr. Poonchand, chairing the Diamond Jubilee celebration, to introduce the ninth speaker of Diamond Jubilee lecture series, and probably the last but one in the series of 10 eminent speakers across the globe. Dr. Rao, it's over to you.
Yeah, thank you very much, Dr. Tiwari, and hearty welcome to all of you, particularly Professor Vipin Kumar, the eminent speaker of today, eminent scientists, dear colleagues, and the young students who are very eagerly waiting for this very interesting talk, I would say. And first of all, I would like to heartily welcome all of you to this very auspicious occasion of the Diamond Jubilee celebrations of CSIR-NGRA, which marks 60 years of dedicated service to the nation and for the cause of science. And it gives us great pleasure to mention that we have had several eminent speakers joining us and sharing with us their great experiences in different diverse fields. And today we have Professor Kumar, who is not only going to talk about water, which is of course a very critical commodity, but he's also going to talk about the very latest developments of handling big data and things like data mining and artificial intelligence and machine learning. So that's the buzzword right now, and everybody is looking forward to listen to Professor Kumar. But before that, I would just like to read a few lines about Professor Kumar. So Vipin Kumar is a Regents Professor at the University of Minnesota, USA, where he holds the William Norris Endowed Chair in the Department of Computer Science and Engineering. He has over 300 research articles and 10 books to his credit, including 2 textbooks, Introduction to Parallel Computing and Introduction to Data Mining, that are used worldwide and have been translated into many languages. His current research focuses on bringing the power of big data and machine learning to understand the impact of human-induced changes on Earth and its environments. He served as the lead PI of a mega program of $10 million, which is a 5-year project, Understanding Climate Change, a Data-Driven Approach, which was funded by the NSF. Professor Kumar has served as chair or co-chair for many international conferences in the crucial areas of data mining, big data, and HPC, including the KDD 2019. Professor Kumar is a fellow of the American Association for Advancement for Science, Association for Computing Machinery, Institute of Electrical and Electronics Engineers, and Society for Industrial and Applied Mathematics. His foundational research is in data mining and high-performance computing, and has been honored by the ACM 2012 Innovation Award, which is the highest award for technical excellence in the field of discovery and data mining, knowledge discovery and data mining, that's referred as KDD. And the 2016 IEEE Computer Society Sydney Fernbach Award, one of IEEE's highest awards in high performance computing, HPC. So with these few words, it's my great pleasure, privilege and honor to invite Professor Vipin Kumar. Sir, it's over to you now, and I am sure you'll be delighted to take a few questions towards the end.
Can you hear me now?
Yes.
Okay, I think I became muted, so let me share my screen again. And please let me know if you could see my slides.
Yes.
Okay, thank you. And again, thank you very much for a very warm introduction. And it's a pleasure to make this presentation on a topic that's, of course, globally important. As Professor Tiwari, Dr. Tiwari said, water is important for sustenance of all life, and it's also critical not just for drinking, but also for production of food, production of energy, and it has come under tremendous stress in recent years, recent decades, and it has really become a grand challenge for the 21st century. And I'm sure people in India, of course, feel this need, but this challenge is faced all over the world, amazingly uniformly. So this is a really big problem. And then let's go through the origins of this problem. So if you look at this since the beginning of the Industrial Revolution, the population has gone up by about a factor of 10, and the per capita use of water has also gone up quite a bit. So overall, our need for water has gone up tremendously, just in terms of consumption. And as a result, there is a tremendous, and there are interactions with climate change, which sort of makes these floods and droughts much more frequent. And as a result, there is a tremendous stress. And I'm just, I'm sure you're familiar with issues in India, but I'm just talking about the United States here. Huge problems sort of that are in progress in all of the Western United States, especially Western and Southern United States. I'm showing you this picture of drought in Southern California. It's going through one of the worst droughts in human history in California. The lake mead, which supplies water to many, many states, has gone on to the levels that have never been seen before. So water quantity, availability is under stress because the needs are increasing and the supplies are becoming more erratic, and it's all over the world. It's, one could sort of go on in different parts of the world. That's one part. So the quantity is an issue because of a number of factors, because of the increase in population, because of the increase in demand for drinking, but also for agriculture, for energy, and so forth. The quality of water is also a challenge, again, all over the world. And I'm showing you, please let me know if you are not able to see the picture, but if you look at the top left corner, you see a big lake Erie. It's the lake which is north of upstate New York, and it borders Michigan, the state of Michigan. And you see this very green area on the corner here. Are you able to see my red mark on the left corner?
Yes.
Okay, good. And when you see this green area, it's algae, and it's a very harmful algae. That means if you drink this, one could die. And if you take a glass of water from that area, you see this, the second circle here, you see the glass, and it has green stuff. It's actually not some sort of a drink, it's actually water from that lake. So this is how the water looks. And why is it happening? Why is the lake becoming such poor quality? Because it's surrounded on these neighborhoods by, this lake is fed by multiple rivers. And these rivers are coming from the areas where people do agriculture. And when they do agriculture, they basically have to put some fertilizers, and excess fertilizers then leach back into the rivers, and then they go back to the lake. And they create these zones, and they create this algal blooms, which are very harmful. And in the oceans, of course, you see them as dead zones in the oceans. And it's a problem that's happening all over the world. So there is a big interaction of human activities, especially agriculture, but other things as well, industrial production as well with water, and that's causing tremendous issues of water quality and dead zones all again, everywhere. And of course, the other thing that is in the news, of course, much more recently is the impact of climate change. You just heard about the floods in Germany. A lot of people died in China and again in India and other places as well. And I'm showing you this picture from Hurricane Harvey in Houston a few years ago. And it's all resulting from these erratic patterns from climate change, changing climate. And it leads to a lot more rainfall in a shorter amount of times. And of course, lots of droughts in some other places. So basically, all of these things have come together to create a challenge for water, for the whole society. And again, it covers all aspects in the sense of it's in terms of how do we have enough water to drink or for consume? Do we have enough quality? And are we going to be impacted by these water extremes like droughts and floods, which of course can be equally harmful? So given this, the question is, what can big data and machine learning do to help in these aspects? And of course, the reason is, just like every other discipline, every other walk of life, there is explosion of data in the domain of water. We have a lot of information about water from the satellite that are scanning the Earth, and I'm going to talk quite a bit about this. There's a lot of information about hydrological cycles from the weather and climate models and from the hydrological models that directly try to simulate the flow of water in these rivers and then the basins and so forth. In addition to this, increasingly, especially in many countries, and I'm sure all over the world, it's becoming more and more common to create this whole water network as a smart water network, in the sense that put sensors at different places. Some of them are direct sensors, some of them are proxy sensors, and as a result, you have a much greater sense of where the water is coming from and where it's going and where it's leaking and where it's being used. So there are all sorts of information like this that's becoming available at different levels. And as a result, it has created a torrent of data. And the idea is that given that this big data has tremendously changed the way we do things in our life, in all walks of life, whether the way we entertain ourselves or we consume information or purchase things or do banking. And the idea is that perhaps the same technology that has tremendously changed all aspects of our life could possibly also be used to address some of these challenges in the big data that I talked about. And I'm going to mention a number of different challenges, but I'll spend a lot more time talking about the specific case study of monitoring the surface water on a global scale, that is being able to figure out exactly what's happening to the surface water, which is the water that we use for drinking, which is the water that's very important for humanity. Can we figure out where it is and how it is changing over a period of time and where it's moving from where to where? And the question is, why would we want to be able to understand the dynamics of water on the globe? And the reason is that we want to be able to understand the impact of changing climate. And just to give you a sense here, in Tibet, here is a lake, Sido-Saka Lake, in 1984 on the top left side. And in 1984, and you can see it's all frozen. You can see white picture. It's an optical image, and just about 25 years later, you can see the same lake. And if you look at the picture, you can feel that all of these frozen lakes have become water, right? So this is the impact of climate change, and you can see, of course, this is anecdote, and you're going to see a much closer look at on a global scale what's happening in Tibet, in the Himalayas, in a few slides later. So you can, if we have an understanding of what's happening to surface water, maybe we can be more aware of impact of climate change like these. The second thing that you see in the top left in the middle is this impact of human actions. Or I'll see, many of you may be aware that it's the largest water body. It used to be the largest water body in Asia. It's in former Soviet Union, and it's a massive lake. It was massive lake in 1989. You can see that. And 25 years later, on the right side, you can see it's only what's left is only a small fraction. And this wasn't caused by climate change. This was caused by human actions. This lake is actually fed by two different rivers, one from the north and from the south. And the water from those rivers was diverted for farming, for agriculture, with good intention. And as a result, these lakes started drying up, and the entire microclimate of the area changed, and it's a big, huge ecological disaster. And this Aral Sea is a poster child because such a dramatic case. But the same thing is happening many places in the world. In the United States, in the city of Salt Lake City, there's a big salt lake, and it's actually going through a very similar transition, not as drastic, but certainly a very similar phenomena is happening there. So basically, humans are capable of changing the dynamics of some very, very large water bodies, and this is just one example of this. And the third thing is, if we have a good understanding of surface water dynamics, we may be able to create better warning systems. And again, I'm just giving an example of a river that happened here in Minneapolis when I was here in Minnesota. Mississippi was flooded, and all Mississippi River all the way from the north to south was flooded. It's a huge river, and this is just showing you, it's pre-flood state and the post-flood state, in which lots of villages and towns were flooded, pretty heavily. All right, and you could use it if you can measure the surface water dynamic. You could actually use this information to quantify the stocks of water, the stocks and flow of water, like how much water we have, how is it changing on a global scale, and how it is flowing from one place to the other. You may even be able to figure out how much water is flowing from one river to the next, and so forth. Information that it's not very easy to share because of national boundaries, even state boundaries. But you could sort of have global information, a pulse of what's happening to water, and that's sort of the goal. And again, such information can also be used integrated with hydrological models to provide much more accurate information for prediction going forward. So this is sort of the big picture. And so the question is, for some of this global water dynamics, what sort of big data do we have access to? And it turns out we have quite a few data sets that we have access to. We have MODIS, which is the scanning the Earth since 2000 on a daily basis. No matter where you are in the world, you look up in the sky at about 10 a.m., you will see a satellite sort of coming up, taking picture of you. Very coarse picture, and the data set is available. It's about each square kilometer has about 16 pixels at 250-meter resolution. And those data sets are made available to the entire world scientific community for no cost. And again, there are many other sensors, Landsat, which takes a picture every 16 days at 30-meter resolution, higher spatial resolution, lower temporal resolution. Then there is a series of Sentinel satellites from European program that have even finer resolution, and actually and every 5 to 10 days resolution in terms of temporal resolution. So there are all sorts of public data sets that are available, and then of course many commercial data sets available that are even more finer resolution, but they cost money. So there's a tremendous amount of data from the satellites available that can be brought to bear to see what's happening to the water on a global scale. Now let's see, given that this data is available, what people have done so far with it. And I just want to give you a sense of what is readily available. And again, all of this product that I'm talking about requires big data, and also, of course, some sort of machine learning or some sort of processing data. And this the state of the art in being able to map water on the global scale sort of spans into two different broad categories. And the left category that you can see here corresponds to static water bodies. So there are many data sets available, starting with a shuttle that NASA flew back in 2000 just to map water on the globe. So the shuttle, there was this SRTM, the shuttle water mission that was launched, and its shuttle just went around the globe for about 2 weeks, shooting radar rays to figure out, to create a data set that was easily produced processed by people to produce downstream data sets, which were static shapes of water bodies. And they have reflected in those are data sets sort of have been produced by many different groups: SD, SWBD, GLWD, Hydrolakes. Hydrolakes is one of the biggest of these data sets. And again, some of them are produced by the same researchers. And it has access, it has the static shapes of water bodies around the world. And it's the most comprehensive data set. Then there's a data set called GRAN, which of course is a subset of that, which only contains the reservoirs, the man-made reservoirs mostly, but the reservoirs of some kind where the water bodies have been, sort of blocked to create some reservoirs. So these are all static water body shapes. They're publicly available. They're produced by people in the hydrological community. And there are hundreds of thousands of such water bodies over the whole globe. Then on the right side, what you're seeing here is so the left side data set tell you what the water bodies are, but not all of them, as you will see. There are many more that are missing that are almost 3 times as many as we are able to find as they are in this biggest of the data set. I'll talk about that later on. On the right side, what I'm talking about is the information that tells you whether water is changing on the globe. But the information is not available at the scale of a water body, but it's at the scale of a pixel. That is, people have used these data sets from MODIS and Landsat and Sentinel, and not quite Sentinel yet, but certainly MODIS and Landsat, to figure out which pixel may be water and which pixel may be land. And if these classifications were correct over time, you could use them to create water bodies. But it turns out that they have a huge amount of errors, and you can't really use them directly to create water bodies. So we have pixel-based information, which is highly inaccurate, but it's dynamic over time. On the left side, we have the static water body shapes, which are pretty good, except that they're incomplete, grossly incomplete, and they don't tell you anything about the time. The objective of this work that I'm going to talk about in the next 10-15 minutes is to capture not only these water bodies, but also their dynamics. So I'll show you a piece of work which is sort of far more complete. As I said, Hydrolakes is the biggest data set that exists. And the real set data set I'm going to talk about at the very end is about 3 times bigger. And so that's one part, that is you have far more water bodies. And second thing is that you're able to see how these water bodies, not pixels, but the entire water bodies, are changing over a period of time. Okay, now why creating such a data set is challenging, because even though obviously there's a lot of data here, and the primary challenge here is because of heterogeneity in space and time. That is, the water bodies, water and land, can look very different in different part of the world at different times. At the same location at different times, it can look very different. So the left side is sort of showing you the heterogeneity. That is, you look at the top 3 lakes here. They're all in Africa, not too far from each other. And the data has been mapped into the same false color composite. That is, the Landsat bands have been mapped into red, green, blue, just for visual inspection. And you can see that the land and water colors look very, very different. This is another way to sort of say that whatever we know where the land is and where the water is in these images, because the dark portions in the middle is water, but how it looks in the spectral space in 3 different regions in Africa is entirely different. And similarly, if you look at the lower 2 water bodies, the same water body at 2 different times, and you can see them looking very different, even though it's the same lake. So this is the heterogeneity part, which means no matter what algorithm that you come up with, it's going to make errors, and people have sort of built global scale products, and they all suffer from huge errors because of this problem. And then the second problem is one of data quality, in the sense that you're seeing these water bodies from the space through satellite, which is pretty far away from the Earth, and in between you have clouds, you have smoke, you have dirt, you have all sorts of particles, and they can sort of create quite a bit of issues. So you can see this animation running on the right side for a lake. It's called Poyang Lake. It's a big freshwater lake that supplies water to Beijing. And whenever you see this very reddish color, that means the data is completely missing. That means data is not even available. You know, it couldn't get processed to be available. So you can see that from this animation that if you watch this area, most of the time I don't even have data. And you can imagine that a lot of the other time when you do have the data, it must be corrupted, which means and then that means you may think you have the data and you're running it through the machine learning algorithm, but you will get garbage in, garbage out. So these are all sorts of issues that are faced by traditional machine learning algorithm. And as a result, one has to sort of develop entirely new techniques in machine learning that can sort of incorporate physical laws and other process level information in the learning framework. This is sort of going to be a theme in my presentation, and of course, you know, of whatever is left of it. So this is something that comes across as a key issue in being able to handle any major practical problem. And again, this is going to be my the only technical slide. Most of the other ones are sort of talking about results. And again, I'm not going to spend a lot of time here given the nature of this talk, but there are publications listed here as well as many more from our website that you can see to get the details. But the idea is, one of the key ideas that goes into creating this global surface water dynamics product is this, we call this approach called Orbit, Ordering-Based Information Transfer, which is a physics-guided machine learning approach, and that helps us create high quality and high resolution dynamics of water bodies, even though the underlying labels produced by machine learning algorithms may be imperfect and incorrect and maybe even incomplete. And it's as I said, this is, and just to give you a sense, I'm showing you two different animations here. On the left side is an animation produced by that's produced by the pixels labels that are available directly from the Joint Research Commission, European Joint Research Commission, and Google collaboration, for which they produce monthly labels for each pixel at land scale, whether it's a land or water. But most of the time, labels are not available. Whenever you see the red color in the animation, the labels are not available. And the green color, it's calling it land, and you can see that a lot of time it's calling middle of the lake to be land. And similarly, it's making mistakes on the outside of the lake. And the right side is the animation. You can sort of see the same information being corrected by this orbit processing approach. So you can sort of get the sense of how this approach is a machine learning approach that can sort of be added on top of the other approaches people have used to make corrections to the dynamics of the water. So with that, I'm just going to now show you, without going to the details, of what some of these methodologies have produced for us. So I'm going to give you a series of these presentations at different level of details. The first one is this system. Actually, this is a link to the viewer. You know, if you're now or later on, you can go just type this link into you type this URL into your browser, and you'll be able to access this surface water monitoring system from anywhere in the world. This particular one monitors all the major surface water bodies that are larger than 2.5 square kilometers, about 10,000 of these. They are represented as a blue dot on this and this viewer. And of course, you can watch the entire globe. It has, and it's presenting the water bodies maps at 500-meter Moody's resolution. That means each square kilometer is broken into 4 pixels of 500 meters each. And the data is available 8 days. That means if you see the time series, it's going to be every 8 days. And a little bit later on, I'm going to show you, using a different viewer, a monthly changes at 30 meters, which is for a square kilometer, you have 1,000 pixels, so much smaller water bodies. And that has, and the second data set, of course, as I mentioned to you earlier, is 3 times bigger than the largest global static water data set available, and also the real set has the dynamics as well. So now coming back to the MODIS based water maps, you will be able to see in just a few minutes for all of these tens of thousands of water bodies around the globe, how are they changing on a local scale, regional scale, or a global scale. You will be able to see the melting of the glaciers in the Himalayas or the shrinking of the lakes. You'll be able to see the changes in the river morphology all over the globe, including India, being able to see where the reservoirs are being constructed, and also talk about, towards the end, relationship between the surface water and the groundwater, which is, of course, a huge concern all over the world, as we are all using the water for agriculture and pumping the water from ground to feed agriculture. What's happening to this the groundwater resources? Are they shrinking? Are we going to be able to reuse them, and so forth? So if you went to this water body viewer, you will sort of see these dots that are sort of showing the different water bodies. If you look at any one of them, this is Don Martin Dam in Mexico, and the viewer would sort of show you the time series going back to 2000 and show you how many pixels that the water body has. And each pixel, remember, is 1/4 of a square kilometer. And you can see that this is telling you this dam had shrunk to a very small shape in 2003 around here, and then it sort of grew up and then shrank again and grew up and then shrank and then so forth. You sort of get the dynamics of this. You see some patterns going all the way from 2000 to 2015. If you use the Google time lapse, and again, this viewer would let you do that. It will automatically show you the Google time lapse images. And then you can see by looking at the date in the time lapse. Time lapse gives you yearly images. And you can see that these images map very well to this time series. So it's a sort of a verification that, yes, what you're seeing in the time series is actually correct. You can see them on an annual scale, not on a daily scale. Because you have a global view of these water bodies, you can actually start characterizing this time series. For example, if they're increasing, you might call them red series. If they're decreasing, you can call them green series. And you can see the moment you color the series on the map for the whole South America, you can see all sorts of areas. You can see lots of red dots. You can see a lot of green dots. And some of these red dots are perhaps because maybe the rivers are increasing, water bodies are increasing there. Many of them happen to be dams. Some of them happen to be green, you can see here, and many of them are shrinking water bodies. We'll see some of them. So there are all sorts of dynamics we can study on a global scale. So I talked to you about this very green area. This is multiple thousand square kilometer. This would be an area, maybe a large state in India. And again, you can sort of see that very large area here has only green dots. And what's happening here? And it turns out that this water body containing about 10,000 square pixels, so you're talking about water bodies alone, consist of thousands of square kilometers. They used to be very large collectively, and then they have shrunk dramatically over recent times. And one of the larger ones, you can see a time-lapse image of it on Google Earth, and you can see that, yes, it's shrinking and growing in the same time. If you watch the ear on the corner here, it will match its ear, and the shape would sort of match consistently with the time series you see here. Now, if you come back to in the same viewer, and if you look at the area near Tibet, you see only red water bodies. You see all of these mostly red water bodies here. And what's happening here? Of course, people have known for quite some time that these glacier lakes are melting in response to changing climate and warming climate. And you can see them on this viewer. You can sort of see these areas that have grown. You see the black areas on this image. The black area is the one which is the lake used to be in 2000, and the red area are the ones where the lake has increased in size. So you can see these lakes increasing nearly all of them. And of course, you can see, and not in one place, but many places. You can verify them with Google time lapse. And because you have all of these, so you can literally create an aggregated chart as to how much of the surface area has changed in water in Tibet, in these glaciers. And it turns out over a period of 15 years, almost 10,000 square kilometer of water has shown up, in that area. So you can figure out exactly how fast it's increasing and what may be happening to it over a period of time. So it allows you to give a very aggregate picture. Before this work, people would create these kind of images for 1 year for a small area. Like they will take a Landsat tile and figure out mapping of the land and water, and then do it 10 years later and see whether these things have changed. So it was a pretty laborious process. Now you have a much more automatic way of doing it available to everybody. You can see the rivers meanderings. This is South America, Amazon area. And you can see that all sorts of rivers, of course, change shapes. This is pretty natural phenomena, but they get impacted by deforestation, and there's an interaction between deforestation and river dynamics. You can also see the same thing in India, for example, and going back to the Indus River. And whenever you have to see these red and green spots, that means water is growing someplace and shrinking nearby. That means river is meandering. And you can see that this is the Indus River sort of meandering in the same place where you see the red and green dot. You can see the same thing in Ganga in Bihar and eastern UP. And then you can see the same thing in Brahmaputra river in Assam and north of Bangladesh. So again, this kind of analysis can be done on a global scale very easily using these viewers. You can see the shrinking islands impact of ocean rise. You can see the construction of dams all over the globe. Very, very important problem for hydrological, ecological impact of these dams. So people study them in hydrology. They actually even have a data set called GRAND, I mentioned to you earlier. And it had very limited coverage of, GRAND was fairly complete until 2000, but after 2000 they had only self-reporting, and then they had only a small number of dams around the world in this group size, about 35 or so. And then because we have this dynamics of all of these water bodies, we actually find far more all over the world. For example, especially in India, GRAND had only 5 in India. And then, of course, if you use our approach, you'll actually find many, many more. Again, this was used only using the MODIS data. Using the Landsat data, we have a much larger set of dams here. Now, this is the other data set I was telling you about. The previous one was about all on a MODIS scale. This is at 30-meter resolution, which means each square kilometer has 1,000 pixels. That means any water body that is more than 1/10 of a square kilometer shows up here. And you can see about 740,000 water, like about 740,000 water bodies are available in this data set below 50 degrees. And this part of the world has only 1/3 of these water bodies are available in hydro lakes, which means this data set is much, much larger, 3 times larger, and has dynamics of all of them. And just to give you a sense of how much larger it is, in India, for example, if you look at all of these dots, red and blue, all of them are in the real sat. But the hydro lake has only the red dots, which basically all the blue water, the dots that you see are missing from the hydro lake. And of course, India is a very well mapped country, but look at the Amazon. This is the north, the Amazon area, South America, and you can see it has mostly blue dots. That means a lot of them are the water bodies that hydro lakes did not even know about. And as you zoom in, you can sort of find out they're not missing only the small ones, but quite a few big ones as well. Look at these large water bodies. And USGS, which is United States Geological Service, which has a very thorough, which is a mission to sort of maintain all of the information on all of these natural resources, and they maintain the water bodies data set in the US itself. And again, the same thing happens in the sense even their data set is actually very incomplete compared to RealSat. What does it allow you to do? It can actually allow you to look at what's happening collectively on these water bodies on a global scale in regions of different part of the world and different countries. And you can see from this curve that on an aggregate scale, a lot of these water bodies have been shrinking in the last decade or so. So that the impact of changing climate and human actions is being felt around the globe. So the first two, so these projects talked about how looking at the lakes and the water bodies. This part of the research I'm just going to talk about in just 1 or 2 slides is being able to monitor the data even at a much finer scale. That is, what about rivers? How about are we able to map the width of the rivers as they are flowing naturally? Remember, water bodies are large. They could be tens of acres, hundreds of acres. So there are a square kilometer, even though they could be as small as 1/10 of a square kilometer, but they're still fairly large. When you're looking at a river could be very narrow. River could have only a few meters of width, 10, 15 meters of width. And the question is, could you measure the width of these rivers on a continuous scale? And why is that important? If you can do that, then you can use that information as a virtual gauge to calibrate hydrological models. Most of the hydrological models have a lot of parameters and they need calibration. And the calibration data is usually used to be used is via gauges. And the gauges, even in the United States, only for a few thousand locations where people have gauges for the rivers. But the areas where you really need to be able to apply these models actually are much, much larger, orders of magnitude larger. And there are places like Africa where there are hardly any gauges available. And then again, the idea is, could we use this data from the remote sensing and machine learning to be able to create these virtual gauges, and that may allow us to do the real-time flood monitoring, assessment of flood risk. And it turns out that even using the data from the Sentinel imagery, which is much finer resolution, 5 and 10 meter resolution compared to the Landsat, it's possible to use some of the sophisticated methods from deep learning along with whatever we have talked about in this talk earlier to create these virtual gauges. and again, this bottom right frame is sort of giving you a sense of that, but I'm just going to give you a data set we created for Ethiopia, where for 57 different locations, and if you see this scale on the top left corner, it's telling you the date. I don't know if it's visible, but the scale is moving. And if you watch the size of these circles, it's changing. And it's changing with the river width. The diameter of the circle is reflecting the width of the river. And you can see this width of the rivers are sort of changing depending upon what time of the year it is. So it is possible to use this technology now to monitor the width of the rivers on a global scale. As a result, you could use not only for hydrological monitoring, but also to figure out how much water is flowing from one portion of the river to the other one, because rivers cross these national and international boundaries, and information about the flow of water across the countries is difficult to obtain. And this is sort of one way to circumvent that problem and figure out how the water is flowing across the world. Last item I'm going to talk, it's one of the last items I'm going to talk about, the relationship between surface water of the dynamics that you've seen so far and the water that is sitting underground, because the water sitting in the ground is being used very extensively for agriculture all over the world in many, many different ways. And that provides us some information, but the GRACE data is available at a very coarse resolution and also only for a limited period of time. So what here we wanted to sort of see whether there is any relationship between surface water, which we can map very precisely now, as you saw, and going back many, many decades, even farther than GRACE is available, and at a resolution which is actually very fine. So if we can build a relationship between these two, then perhaps we'll have a better sense of what the groundwater may be. And then, of course, GRACE is also providing a proxy for the groundwater. And what you're seeing here on this chart, on this slide here, is a correlation between the time series created by GRACE. And again, this time series is created by GRACE in a very coarse resolution space. Each pixel became a degree by degree. We got the GRACE time series from a standard database available publicly. And then we took all of the surface water bodies in that degree by degree space, aggregated the area, and then we created a time series. So we have 2 time series for each location at a degree by degree resolution. And what you're seeing here is the heat map of the correlation. And in this one, I would urge you not to pay attention to any area above 50 degrees, because these are the areas that are very cold. And sometimes because of snow, when this map was created, these time series were not accurate for the upper area. But areas below this line are pretty accurate. So whenever you see a positive, when you see a red dot, it means the GRACE time series and the surface area time series matched very, very heavily. Red means they had a correlation of more like 90% of the correlation. So very, very heavily correlated. You will see them. And the interesting part, and most of the part you can see, are highly positively correlated. Many places you will see this blue correlation, which means it's highly negative correlation. So it's almost like minus 0.9 correlation. So you see this correlation extending all the way in many places. And these are pretty interesting stories here. So I'm going to show that to you. So basically, the GRACE and the surface area tracks very directly. And you can see here, for example, there's a location in India, which is a red location. And you can see the correlation is 0.9. And the blue you can see is the surface area map here. So in this lower map, the blue represents the surface area variation computed using our algorithm number of pixels. And the red one is coming directly from GRACE, the public website. And you can see that these things are going up and down. So this is what you would expect. The interesting thing is we didn't expect such a high correlation between surface water and groundwater, but looks like the surface water changes are a high proxy, a great proxy for the groundwater. So that's one good news. Second thing is that if you look at these blue areas, which are the correlation is negative, you see then here, this is all of this, the northeast area of India, Punjab, and even extending some parts into Pakistan. And you can see here, the surface water body areas are increasing in these areas, and the groundwater is decreasing. And what's happening here? It's basically most of this area, not just in India, but all the way up to Vietnam. This entire area, if you go in and then if you zoom in from the satellite, you will find aqua farming. It could be rice farm, could be fish farms. People are, pumping water maybe from the ground, maybe, or maybe they're just collecting rainwater and it's evaporating. So basically, this entire region in the world has this negative correlation between the surface water and the GRACE, which means, and all of this area is also unique in using the aqua farming. So you can sort of see the impact of human actions on what may be happening to the groundwater. And again, this is showing you in Bangladesh, in Thailand, very similar pictures. Now, this is my last slide, so we can finish on time. So I talked about the ability to map surface water. So we have a sense of what the water bodies are, how they may be changing. And because we know these water bodies and how they've been changing all across the time, we can actually characterize them. Are they man-made? Are they used for mining? Are they reservoirs? Are they a sort of natural lakes? So we can actually, it turns out, using downstream machine learning tasks, which we are working on in our group, we can actually do quite a bit of characterization of these water bodies, which can help us further understand what's happening to the ecology of the water on a global scale. So that's one part. Second thing I talked about, and of course, for this part, I talked about our work at different resolutions and using MODIS data at 500-meter resolutions, using Landsat data at 50-meter resolution. The RealSat link that I provided on the previous slide is publicly available. Anybody, anywhere can download that, all of those 750,000 water bodies from anywhere in the world. And similar technology can be used to even look at much, much smaller water bodies, even as tiny ponds in your backyard, because Sentinel makes it available to let it go down to 10-meter resolution. We're still talking about free data that's available freely on a globe. So all you need is some computing power to create dynamics of those smaller water bodies. And of course, once you go down to data that you can purchase, which are sub-meter resolution, you can go farther, but of course that's expensive, but the methodology would still work. So that's one stream of work I talked about. The second stream of work I talked about was being able to monitor the width of the river. That the challenges are much severe there because you're looking at much finer changes in the water bodies and on a much faster scale, but again, tremendous success there. That's the second thing we mentioned. Third thing we briefly mentioned, the relationship between the surface water and the groundwater. Then there are a whole bunch of other ways in which the machine learning and big data can come together to address some of the challenges we talked about earlier. And one of the big ones is being able to understand the interaction between land and water. I mentioned to you about this harmful algal bloom in Lake Erie earlier, in which the water gets toxic to drink because of the interaction between agriculture and the water. And it's not just Lake Erie. The entire watershed that supplies water to Washington D.C. Again has the same issue. That is, the water sort of gets contaminated from the polluted urban areas where the rain falls and the dirt collects from the neighborhood areas and then goes into the rivers, and then it sort of creates a challenge for the water quality. Again, I'm talking about cover crops. Cover crops are a solution that are being promoted for changing the agricultural practices, especially in the Western countries, where in the colder countries where the crops are only planted during the summer, and in the winter time, in Minnesota, for example, there'll be no crops. But with the changing climate, a lot of rain falls in April and May, and as a result, all of the fertilizer that people put in a year before then leftover just get washed over into the rivers. And how do you sort of manage that? becomes a problem on a global scale, and then people are talking about being able to plant cover crops. And again, many of these technologies we're developing sort of are sort of looking for a solution to that problem. And more importantly, developing this new breed of models called hybrid physics data models, which can use the machine learning and traditional physical process-based models to combine them and make them more powerful. And this last paradigm, of course, is sort of originated all of this work, and it's one of the dominant direction of work in our group. And this general topic is now called knowledge-guided machine learning. We held a workshop last year on this topic, and we had about 1,000 people register from all over the world, about 30 plus countries. And the second edition of this workshop is going to be held on August 9th and 11th, August 9th, 10th, and 11th. And those of you who are interested, I encourage you to go to this link at the bottom. And it's a free virtual workshop, but you have to register for it to be able to get the link. And it'll provide you a lot more information. We have about 35 different talks from all over the world on 3 different days. Exciting program, mostly focused on bringing machine learning and process-guided knowledge together. So with that, let me stop. I think we're almost out of time, but I'm happy to take questions, and I'm happy to stay longer than the end of the hour if necessary. Thank you, and I'm going to stop here and perhaps unshare my screen so people can see me.
Thank you very much, Professor Kumar. That was not only very interesting, but very promising lecture, I would say, because as you know, the National Geophysical Research Institute is a data-driven institute, and practically every scientist here works with decades of data at very high precision. So I think a lot of new ideas have emerged from your presentation, and I am sure people have really enjoyed. I thank you very much for accepting our invitation and delivering this wonderful talk. And I would like to express a few feelings from my side that, some of the data sets that are worked upon, they have a very fine sampling scale compared to, for example, what you have shown. Most of the geoscience questions are based on data that comes from satellites, which have a very, very coarse sampling. So when it comes to machine learning or artificial intelligence pertaining to specific events, like floods, for example, a flood starts in the morning and it's over in a couple of hours. So it's probably not adequate to have the satellite data to address this kind of issues. But I'm actually glad to share with you that we recently started to look at seismic data, which records all these mechanical disturbances from floods and glacial retreats and things like that. So I was feeling that maybe seismic data kind of fits into the gaps which the satellite data has. So this was some of my thoughts while attending to your talk.
So very good observation. So again, let me just repeat what you said earlier. You just said now that the data from the satellite is at a resolution that may appear to be not as useful for monitoring events that are occurring very rapidly, like literally in a matter of hours. Okay? So and let's come back to that. So I have 2 responses to that. One of them is that the satellite technology has changed dramatically over the last 40 years. Okay, so from the Landsat to MODIS to Sentinel to QuickBird to Planet, and then there are these geo series of satellites which actually they can be directed to one location on the globe and give you information every few minutes. So what I'm saying that the way data is being collected and generated even from the satellite is actually changing pretty dramatically. Something that people could not have thought 20 years ago or even 10 years ago is possible now. So that's one part.
Right.
The other part is that even if you sort of, let's assume that we had only data from Sentinel, which is the finest resolution data set you can have in public domain, everything else you have to pay. Even using the Sentinel data, it would be possible for you to look at the historical data and figure out how to calibrate your hydrological models. And once those process models are calibrated, then they have a better chance of responding to these quick events. Because if I don't have the fine resolution data, then the only thing I have to do is use my hydrological models. but these models have parameters, and if you don't have them calibrated properly, then they're useless. Right. So what I'm saying, that there are multiple things we have to bring to bear. One is we have to use the data that we have, right? Unfortunately, even the data is getting better in the sense 5 years from now, maybe the geosat technology would be even so advanced that if a flood is happening, somebody would launch a satellite, would point a satellite there, and then you'll have a minute-by-minute data, right? People are using it for fire and other things as well. Right. Second thing is, even in absence of that, if you can improve the calibration, and again, you work in geosciences, people work with inverse modeling here in geoscience. Inverse modeling is a big problem. And the counterpart that is model calibration that people do, and these are two different problems. People did them very differently. But using machine learning, both of these directions are actually coming together in the sense that, can you use machine learning to improve calibration? Can you use them to improve the solving of this inverse problem by bringing in data? So there's a lot of activity there. It's a fast emerging area in the sense that these are the topics we're going to be talking about at this workshop, in about 2 weeks from now. So what I'm saying, that there's a tremendous moment in this direction to address some of the issues that you talked about. That is, there are real issues, and yet there's a hope.
Right. Yeah, absolutely. Yeah. So maybe we can have a couple of questions. Dr. Tiwari wanted to ask something.
Yeah. Thank you very much. Wonderful talk. We always listen something new. I just wanted to really learn what are the physics-based algorithm are being used in the image processing, because even without physics-based learning, we were able to get the similar kind of answer. So why do we need the physics-based learning in the image processing?
Okay, all right. So if you look at the traditional machine learning paradigm, and if you look at the basics of these algorithms, they're essentially finding patterns in the data that's made available to them. So they're at the core of it, they are statistical learning algorithms. Of course, these algorithms are very sophisticated. They've become far more sophisticated than anyone could have imagined, even in the last 2 decades, right? So the oldest algorithm you could think of is regression, and then as you sort of improve them, you have the Bayesian methods, you look at them, the decision trees and the support vector machines and the neural networks of the 1980s, and then the deep learning methods. So they're successively more powerful frameworks that are finding information in the data, but essentially they are relationships that are picked up from the data. Okay, that means if I give it a data that is very different than the one that it has seen before, there's a possibility that it will make mistakes. So if I can use the most powerful deep learning algorithm and give it a lot of data and have it produce what is water and what is land, it will sort of give you, it will learn the relationship. But if I give it completely different set of data, then it wouldn't be able to sort of work there. Now the physical model, the process models, as long as the physics is right, as long as the parameters are right, you can feed them any kinds of weather patterns, and they will produce data which will be physically sensible. So basically, we have 2 different extremes. One, if I have a lot of data, I can actually learn patterns. If I have all the representative data, I don't need to do anything else. And you see the success of those methods in language translation. Back 40 years ago, people were building linguistic theories to do the translation, and they could not go very far. Today, you take your iPhone, you can take your smartphone, and if you have the right app, you can map it, you can point it to any language text, and it'll convert it. It will do a pretty decent job. You cannot do that kind of translation using the state-of-the-art linguistic theories. It's all made possible by the very large amount of data set. But on the other hand, physical models are trying to make predictions in a physical setting, and then if you use some of these techniques, and if you don't have all the representative data, which is very rarely possible to have, then what happens is that these methods can make predictions that are completely wrong. And you may have heard of this failure of Google flu trend. Google flu trend was designed to basically predict the outbreak of flu in the United States by looking at the queries people type on Google search engine. And for the year it was designed, it did a fantastic job. And then pretty soon it started mispredicting. So you need methods that can also bring in the power, the process-based knowledge of the physical phenomena. You're trying to make prediction of the physical system. That physical system follows certain properties, and if you're not aware of those properties, then you're leaving something on the table. So basically, being able to bring those physical properties inside a machine learning algorithm can make it more robust, can make it more easy to generalize to out-of-sample scenarios, can make it produce results that are consistent and more useful and trustworthy. So this is sort of the big picture answer to your question.
Thank you, Professor Kumar. We have Professor Csir-Ngri would like to ask.
Yes. Yeah. Thank you for a very fascinating lecture. You partly answered my question in the previous statement that you made about processes. When you talk about future, you are looking at water volumes and not water surface areas. So I did not see a mention of two things in your talk: bathymetry of the water bodies, that is important, and the amount of water lost through evaporation.
Okay.
That's first question. Okay. Anyway, you can answer that. I'll ask you one or two more.
All right. So very good points. The ultimate thing is the water volume, in the sense that the most important thing is how much water we are losing, right? Okay, so surface water is a proxy for that, in the sense that if you have the surface water and if you have the elevation information, then of course together you have the volume, okay? And so elevation is possible to get from the digital elevation maps, which of course are not very good quality. But by the way, when I mentioned that the surface water mapping technique that I produced are physics guided, they are physics guided because they create their own implicit bathymetry. So they're not the real bathymetry, because the real bathymetry requires digital elevation maps. So all of these maps that I showed are produced using only the satellite images. But one of the intermediate process in the production is to create a virtual bathymetry. Okay? So this is not the actual bathymetry, but it's a virtual bathymetry that is produced based only on the images. So and you can actually produce a relative bathymetry by making some assumptions, and that's actually what leads to all of these fantastic results all over the globe. So bathymetry is being produced, but not in a way that you would like, but it sort of helps you create this good surface water maps. In combination with the DEM, it can provide you very direct information about the volume. But much more importantly, just another connection that you may be thinking about is, how would I use this information to find out how much water is flowing through a river? So one of the very big thing is how much water is flowing through Brahmaputra between China and Assam. How much is flowing through Assam and Bangladesh? For example, you can take any river that crosses any national boundaries anywhere in the world. Now it turns out that if people in hydrological community have built mathematical formulas that if you have a river and if you know the width of its river at multiple places that are not too far from each other, then under certain assumptions, you can find out the amount of water that's flowing through them. So it turns out that if you use some additional assumptions that are reasonably formulated, you can actually, the ability to measure the width of rivers at different locations at different times can also be translated into the amount of water that's flowing through it. And it's a much more complicated discussion. I can send you to the paper, but what I'm saying is that those are downstream applications that are made possible by this work.
And how would you take into account the water loss due to evaporation when you are calculating water security issues?
Okay, so
which could be significant. In India, it could be 2 meters of potential evaporation.
Precisely. And I think that those are the kinds of issues that we are working with USGS here in the USS itself in a very similar way. That is, they're trying to model the entire hydrology of river basins, and they're measuring the temperature of these river streams, the flow, and of course, some of it correspond to evaporation. And for that, you bring in the process models and then you guide them using machine learning. So basically, the evaporation and such would be actually handled using the process model, but you calibrate them or you make them more informed using machine learning. So there's an entire series of papers we have in our group on process-guided machine learning for monitoring these surface water bodies. So again, and all of this work is focused on United States right now for being able to figure out the temperature of these lakes and water bodies at different lengths, surface water temperature, and their water quality. So these are some of the issues, of course, will be talked about in the workshop 2 weeks from now.
Thank you so much. I have many questions, but I'll stop here and let others ask.
Right.
Yes, okay. Thank you very much. Next question, Dr. Prakash Kumar.
Yes, thank you very much, sir, for this such an informative talk. But I have a small, two small queries, because you have picked maybe millions of data points all over the globe using satellite, but probably some of them will be irrelevant features, which may not be useful for your training the data set, training the algorithm. And the second, sir, connected query is that how much data will be sufficient enough for training either a supervised algorithm?
Yes. Excellent questions here. And again, if you had, if somebody could guarantee enough representative data, then machine learning algorithm would work, right?
Yes.
Okay. But the question, how do you guarantee that?
Yes.
And this is where the marriage of physics and machine learning comes together really well, in the sense that if you bring them together, then you can work with a lot less data. So on I showed you the results on the MODIS-based product. Remember for the entire globe. So MODIS had about almost 1 billion points on the whole globe, and as you said, most of the points are not relevant.
Yes.
Right. So all of those results were shown by building a single, very simple machine learning algorithm that had 1 million pixels observed on certain dates, in the sense that not even the same pixel observed on multiple days. So basically, about a couple of hundred lakes were selected.
Yes.
And some points were selected from those lakes and their neighborhoods.
Yes.
And then those were used for training. So it's a very small data set. Okay. So. Yes. And that entire data set was used, and the data set, of course, was not perfect, because when you use a machine learning algorithm, and if you build the locations of land and water, you'll find a lot of errors there.
Yeah.
But this algorithm that combines this information with with this physics, with virtual bathymetry, fixes all of those errors.
Yes.
And same thing we did for the second project, which is the real stat, which is so the amount of samples used were very few, but the errors were corrected using physics.
Okay. Yes.
Right. So this is exactly the power of bringing physics and machine learning together, because you can leverage them together as opposed to have to worry about the limitations of each one of them.
Okay. Thank you, sir.
Thank you very much. There are lots of questions, and I don't think we'll be able to cover all of them. But I'll just pick one or two, Professor Kumar. I hope that's okay.
That's all right. Yes. Okay.
Before that, maybe I would like to just read a comment that has been made by Professor Ramesh Singh. His suggestion that NGRI should plan to use drone with hyperspectral sensors to monitor small water bodies and small areas. So he has made that suggestion. And there's another question which asks whether it's possible to trace contaminants. When you are mapping water bodies, is it possible to trace contaminants with the use of ML?
So again, there are two possible approaches if you are trying to track contaminant. One of them would be the remote sensing, and one of them would be the process models. Remote sensing, you can only track anything that's visible in the spectral space. And there are, for example, people would track harmful algal blooms, and of course on a large scale from the multispectral data, right, using Sentinel and others. But if you are actually looking at the flow of contaminants through the water bodies, the best way to do is to use process models and guide them using machine learning. So it's called the process-guided machine learning models. And that's, as I said, is the whole series of work in which these models, because they have so many parameters, by combining machine learning and process-guided models, you can actually make them much more powerful and work with much fewer samples. So I would say for contaminants, the promising approach would be process-guided machine learning, not just remote sensing-based machine learning.
Right. And there's a question which asks, how do you handle the very important issue of varied data accuracies? Like you are dealing with lots of data which have different qualities. So
exactly. And yes, and that's actually very good. So I didn't mention to you about this virtual bathymetry operation that's done, and that thrives on it. If you have lots of data And even if it has errors, the overall errors sort of get averaged out. You may have heard of this mechanical Turk. People use these images and you get them labeled by people, all over the world for very little money, and you cannot trust any of them. But because all of these people are making mistakes, but they're necessarily uncorrelated, so lots of data coming together can actually lead to better information, even if a lot of it is incorrect. And so those are some of the principles that sort of reflect into construction of this virtual bathymetry, which then improve these algorithms. So basically, indeed, the data is wrong, and you have to figure out how to work with the data that happens to be wrong quite a few times. But it has some information. Actually, if you watch this KBC show, the Kaun Banega Crorepati show, you see the audience participation, and each one of the people in the audience, none of them are experts, right? And very often, if you ask them the right question, the majority gives you the right answer. And you can sort of tell. So basically, for some questions, if you ask a lot of people, and then even if each one of them has very little information, the majority worked. So that's the same principle works in big data. That is, if you have a lot of samples that are all erroneous, but there is some information there, and it actually works pretty good. So the same principle actually works in machine learning in a very constructive way.
Yeah, that's very interesting. Yeah. Actually, I'm getting a feeling that even without understanding the physical process, it is perhaps possible to teach the machine or do the machine learning. For example, if you have scores of ECGs, you provide the ECG records, a huge data set of ECG, and you also provide the data of who gets a heart attack. So probably the machine can predict who is going to get a heart attack. I mean, I may not even know how to look at the ECG. I may not understand the process, but with the huge amount of data, perhaps it's possible to go for machine learning. It looks like
that's right. But what I would say is that indeed that's possible. But if you bring in the physiological knowledge inside the framework, then you can make this prediction process a lot more robust. Because right now, maybe you took the data from a certain sample, and maybe that relationship between ECG and the heart attack does not translate to a different group of people or to a different ethnicity, or maybe different sort of images. But if you use the process-guided information, then you can make this entire prediction process a lot more trustworthy and a lot more generalizable. So,
right.
So there is a promise of machine learning, but there is also a peril because it can fail miserably on unseen data sets.
Yeah. People can misuse actually.
Yes.
Yeah.
It can be misused, or it can also fail in a way that's very unpredictable.
Yeah. So perhaps we can close here. I think it's already nearing 8 p.m. here. So Dr. Tiwari, is that okay?
Yeah, I think it's fine. If there are some questions, we can send email and get some reply from Professor Kumar.
Yes.
Yeah, so I think we should really profusely thank Professor Kumar for not only an interesting, but I think it's the most relevant topic as on date for any geoscience institute. And so thank you very much, Professor Kumar, from my side and on behalf of Director and all the scientists of this institute. Thank you very much for this lovely lecture. I think a lot of takeaway things for us in this lecture. So I would hand over to Dr. Tiwari. You would like to say a few words?
Yeah, I would also like to make a comment that we have been trying to start some new program, including geophysical data analysis, and Professor Kumar has also agreed to help us particularly towards the physics-based learning part, because we know that the inversion models are mostly physics-based and the statistical models are data-driven. So marriage of these two, particularly for the large geophysical data, seismic data, where we all know that, for example, full waveform inversion takes endless time on the small machines, and large machines are having very expensive maintenance. So that kind of plan we are planning to implement, and Professor Kumar is agreeing, and we will have several further interaction. We look forward for much more knowledge gain from his experiences and use of the machine learning process, guided machine learning, physics-based machine learning towards the geophysical applications. So now the deep learning or other algorithm, ANN and all that, whatever is used are what Professor Kumar today has educated us. We will take it to much deeper in the earth, and would like to image the earth with these large data. And we were also thinking that if we can bring the process in that. So there are very heterogeneous data sets, and there are data which are being used simultaneously to find out a physical model of some area, for example, subduction zones, and parallelly see the dynamic part of the subduction zone together. And so predicting the process and the consequences of that process with time. So it's going to be a very, very interesting thing, and we look forward to work together, and I'm sure the colleagues who could not interact may get several more other opportunities to interact. So with this, we would be really very much appreciating not only the talk, the excitement what Professor Kumar is bringing, but also the promise what we see that we can do together using the computer knowledge and the experiences of the physical data, imagery data. Another problem which will be of the great interest for the country, and we will be able to work together, which we discussed while the Bible meeting have for the India-centric hydrological models, as well as the use of NISAR data. You know, NISAR data it is the mission between India and US, NASA together, which will be providing the INSAR data of much higher resolution than ever had over the Indian region. And time period, I was told that even for 1 day data for the India is almost like 3 teraflops. So terabytes, and the kind of the process required to deal with such kind of the data in the real-time domain, if as you are mentioning day-wise or hour-wise, it will be a Herculean task to deal with supercomputer as well. So we are very much really lucky to have a person through the new initiatives of Bible at the very right time of this juncture of country. So on the behalf of all my colleagues, many of the people from the different institutions of the country, and particularly the young researchers, we once again thank you for making our evening good, and though your morning must be a little tiring to get up so early and start with. So thanks a lot, and look forward to
It's a pleasure. Thank you again, and I'm happy to be part of this group. And
thank you, sir.
And good luck with your proposal, and I'll look forward to hearing from you.
Thank you.
Okay. Bye bye.
Thank you. Bye bye.